Okay, so let's look at an optimization problem which is classified as an unconstrained optimization. So that at a minimum, what you need in an optimization process is a cost. And you want to minimize a certain cost or certain function. Okay, let's say that there's a function which is a function of two variables, x1 and x2. I'll write it down as 100 x2 minus x1 square plus 1 minus x1 square. Okay, so this is some function, and we want to minimize this function. Okay, it's also sometimes known as a cost. So to minimize the cost, you could also have a maximization problem, in which case you're maximizing the cost. The function we're going to use in MATLAB, in Python, sorry, is actually minimized. So there's a way to convert a minimization to maximization. So for example, if there is a minimization of f of x, and f of x is, in this case, f of x, you can see it's basically, I forgot something here. It is basically quadratic. So it's always positive because you can see it's square of two terms. So it's monotonically sort of increasing. It doesn't show crazy behaviors. Then you can actually minimization of f of x is equivalent to maximization of minus f of x, or maximization of 1 divided by f of x. They'll have the equivalent same solution. Okay, so how do we solve a problem like this? Ways to solve. Okay, one is a graph of f of x versus x. So if you actually draw a graph of f of x, which is on the z-axis, and let's do it this way: x1 on the x-axis, x2 on the y-axis. Then you will see, and I think I have a plot too, that this function looks something like this. There is actually a clear minima at x1 equals 1, x2 equals 1. So x2 equals x1 equals 1. Okay, in this case, this is just by doing a plot. Now, the plot is really hard to do in more than 2 dimensions, or more than 3 dimensions. It's really hard to plot something which has 3 variables, because now f of x is z, but how will you show x3? So the other way which people can do this, and a lot of engineering is on guesswork, and trust me that guesswork is a good thing to have, but you need to check your guesswork. So here it turns out there's something nice about f of x. F of x is always greater than 0. It's a sum of squares, as you can see. So the minimum value of f of x is probably at x equals f of x equals 0, right? Because f of x cannot take a negative value, because it's a sum of 2 square terms. So if we go with the assumption, so this is actually our guess. We're making this guess based on, I would say, domain knowledge. You know something about the cost. So if you make this guess, we can then say, when is f of x equal to 0? Well, f of x is 0 when both those terms, which are in the quadratic, are actually 0. So here, x2 minus x1 square equals 0, and 1 minus x1 equals 0. If you solve this two equations, you will see that here, for the second one gives you x1 equals 1. And if you put 1 equals 1 over here, you get x2 equals 1. So here is something to do with our knowledge. So we know something about sum of squares. We make a guess. That guess has to be checked. and we get this value. Now, it could be that if in a scenario where you are trying to do this optimization, you cannot have a value of 1. In fact, x1 has to be greater than, let's say, 2. Okay, that that is a constraint. So those constraint optimization will cover next. But if you don't have x1, you're not allowed to have x1 less than 2, then what you can do is you can then start saying, okay, now x2 is 2. So what is x1? And sort of go back, work it out backwards. Right. So there is a constraint which I'm not really talking about right now, but we'll get to that. So this is the second way of doing it, and totally valid approach. A lot of things in control systems relies on making cost or assuming a cost which is quadratic. And once it's quadratic, it's super easy to solve it. So sort of change the costs so to suit your purpose. There are also ways in which you can sort of bound, if you have a cost which is not quadratic like this one, sum of squares, then you can basically bound your cost such that it is quadratic and do it. And there are like there's a whole course offered at UIC on convex optimization, which is basically this kind of optimization. Okay, so that's the second way. The third way, and which is the way of Python or numerical programs, is when f of x, if you want to achieve a minimum on any function, you need to check the derivative. This is the called the extremum. You have to basically check if df dx is equal to 0 and solve. So solve for x. And then the condition is that if d square f dx square is greater than 0, then minimum, solve for, I'll call it x star, minimum is at x star. If on the other hand, you found that df square dx square is less than 0, this is minimum, that is max is at x star. So this gives you, this is the calculus condition on achieving optimum. Okay, so this is how you proceed. Now, not all expressions can be written. You can find a derivative. What if the cost function was a result of an optimization problem? So for example, if there was a torque and the cost was torque square, well, it was torque equals a PD controller, then it's not sometimes possible to find an analytical expression for that. So that comes from a simulation. So there are ways in which a simulation can be used to figure out the derivative, which is basically what they call finite difference. And then you can find a finite difference of d square f dx square to prove its minimum or maximum. So all these things are done inside this optimization function called SciPy. It's in SciPy. This is an optimization package, minimize. So we'll be using this function for optimization. Okay, so it actually turns out that it's this, you've seen this before. If you think of f of x as g of x, df dx, so it's actually doing root finding on g of x. So root finding is fsolve. If you remember, we did fsolve for ik. So really what optimization does is it finds the first derivative, which can be done by numerically derivatives or analytical, and then find the roots of that. So because f is non-linear, it actually, there are ways in which you approximate that with a linear or a quadratic approximation. You check, find the roots. Because you're doing an approximation, you don't have the accurate value for the optimum or accurate roots, and you keep doing that. So it's really not easy to do this by hand, but clearly it's possible to do this with an optimization package. So what we'll do is we'll use this, and I'll show you how to do this with scipy.minimize. Okay, so here is scipy.optimize. I need to install this if it's not there, so you can do Python pip install to install scipy. The cost is the same one I wrote down, x2 minus x1 square, the whole square, 1 minus x1 square. And it's as simple as doing minimize, telling it what the function is. All optimization softwares require an initial guess because they deal with numerics rather than analytic expressions. So I need to give an initial guess. I just gave 1 and 2. And then there's a method, which basically there are lots of methods. We can look at the documentation. So here is the run, which should give me x1 equals x2 equals 1 if everything works right. Okay, so here is 0.9999, 0.9999, which is almost equal to 1. Now you could try something out, like for example, 100, just putting something really far away from the optimum and see if it still gives you. It actually gave you 42.791830, which clearly is not the optimum. So there's always this problem with these methods, which is they're usually local in the sense they can give you solutions close to the optimum, but then you say, if it's close to the optimum, why use this, right? It turns out that it's not so bad. This is really far away. Also, it's dependent on the method. Some methods are better than the others. So let's try decreasing the factor of 10, and let's see if it gives optimum. So it did not give the optimum for 200, 100, but it did give an optimization for the correct value for 20 and 10. Now, what people do is if they get something like this, you obviously check for the optimum by, there's no way to check, right? Because you don't, let's say you don't know the solution, it's very complicated. You basically put this as an initial guess. So we got from using 100, 200, we got this value. So then what we do is we run this a few times, 42.79 and 1830 as the initial guess. And I suspect that this is going to go haywire. It might go to, well, it did actually give you the optimum. So it just turns out that if you want to check if an optimization actually is giving you the right value, you can take the solution, run it through the optimizer again, and see if it actually converges to the same value. If it does, it probably means it's a global optimum, so it's the same solution no matter where you start, or it's a local optimization if it keeps switching between different values. So let me just put this back to something like this. Let's ensure that it runs. It worked. Okay, now let's get to the second part, which is unconstrained or constrained optimization. So this is the more useful one, as you'll see. Okay, so in this case, I'm just going to go with an example. We want to minimize f of x, where f of x is x1 square plus x2 square plus x3 square plus x4 square plus x5 square. So it's a optimization over 5 variables. Okay, and if I give you that problem, you say that the optimum is x1 equals x2 equals x3 equals x5 equals x5 equals 0, but now there are going to be constraints, which makes that optimum not true. So we're going to put constraints. X1 plus x2 plus x3 equals 5. So clearly, if 0, 0, 0 was the solution, then you will not satisfy that constraint. Then we have x3 square plus x4 equals 5. We have constraint. So those two are equality constraint. Here is inequality constraint. x3 is less than 5. And there's another one on x4 square plus x5 square less than 5. Okay, so there's some names given to it, and they're kind of obvious, but let me just give you the vocabulary. This is a linear equality constraint, because the optimization variables x1 is appearing linearly. This one is a non-linear equality constraint. Okay, on these lines, this one would be a non-linear inequality. Okay, now there are two more. These can be treated as linear equality constraints. Inequality because of the sign of the greater than or less than, and then linear because they only have x1, x2, they don't have any squares or signs, and something non-linear. But the better way to deal with these is to treat them as bounds. So it's saying that x1 takes a value from 0.3 and less than infinity. So it's positive and greater than 0.3. And this one, x3, is between 5 and negative infinity. Okay, and which clearly means that x2, x4, and x5 have no bounds. So they are technically between minus infinity to plus infinity. Okay, so this is how you would set up the problem in scipy.minimize. You will specify a cost, and I show you how to specify all these constraints. Always try to put bounds. It makes the life of the optimizer easy. And then there's a way in which they deal. Some of the optimizers want you to specify the linear equality constraints separately from the non-linear equality constraints because the methods which I use deals with them slightly differently, and some really don't require. So I'm going to show you two ways to do this optimization using minimize. They differ in the method used. So here is the first one. This one uses the same minimize. Okay, this uses a method called SLSQP. It's called sequential quadratic programming. It's a method where you approximate the cost function with a, it could be non-linear, but it'll approximate the quadratic cost, and then it will do the optimization. Let's see what this is. How do you specify the constraints and the bounds in this? So there's a cost which is clear. It's the sum of squares. And remember, I go from 0 all the way to 4 because there are 5 variables. This one requires me to specify bounds, which are in the variable called limits. If you go to limits, I said the first and the third one have bounds, and the other ones have minus to plus infinity. Then we have constraints. It actually I've split it into equality and inequality constraints, but really you can mix them up. SLSQP does not really require them to differentiate. I split this up just for my own purposes. So here we have equality constraints. Oh, by the way, I'm sorry. It actually wants you to specify equality and inequality constraints so that it can deal with them. Actually, no software wouldn't want you to do that, right? Because there are clearly restrictions on them. So equality constraint, we have x0 plus x1 plus x2 minus 5 is equal to 0, and then this is equal to 0. So this is the function is called, I think, lambda x. I think that just means it's the input. And then this one is the inequality constraint, and it requires the inequality constraint to be specified as something greater than something less than 0. We can check this quickly. I'm not too certain. Let's go to scipy, optimize, minimize. Okay, so here are all the methods. Remember, we've used BFGS for unconstrained. We have used, in this case, SLSQP. There are lots of things you can pass through this function. I think it requires you to specify the constraints as greater than greater than equal to 0. Okay. Okay, we can understand from my code itself. Don't have to really deal with this. So if you look at my code, look at how I specified this inequality constraint. I specified as 5 minus, I remember 3 is actually 2, so 3 is actually 4, and 4 is actually 5 because indexing starts from 0. So this is saying 5 minus x4 square minus x5 square is greater than 0, right? And if you look at my, we just rewrite this. So we can rewrite this as, so first I take this in on the left side to subtract both sides by 5. I do a mistake here. in the code. Let me see. X. Okay, it's right. So x4 square plus x5 square plus minus 5 is less than 0. So in order to change it to what it is in the notes in the code, I need to multiply both sides by -1. When I multiply it, I'll get 5 minus x4 square minus x5 square is greater than 0. I need to flip the sign. So this is how it expects you to give it. You need to give whatever the inequality always should be specified as greater than 0. That's how the convention is. Some softwares like MATLAB requires to specify it like this. Some require it to specify it like that. So if you go and check here, the code there is actually requiring you to do that. It should be obvious from the documentation, just that I did not go through it in the lecture quite in a slow fashion. Just check this. I think the functions will tell you how to specify it, but this is specified as a greater than rather than less than. So here are some initial values, and let me run this. Okay, so it's giving you some information which I printed here. The other one also gives you, I did not print it. It says that the value is 11.27. The minimum, it took about 7 iterations. So 7 times it went through this process of linearizing the equations and computing. It needed 43 function evaluations. So it calls this function f of x, which is right here, 47 times. If you have a very expensive function cost, that will add to the time it takes. So you need to be mindful of that. And then, of course, the gradients, it needed 7 gradients. This is the optimum. That's what it thinks. The way to check this is you could take this, make it an initial guess, run it again, and see if it gives the same value. If it does, then probably it's the optimum. You could also change this to another value, different values inside x0, and see if they still give the same root. I'll not do that. Let's go to the other one. Here's another way to do this. This one uses a method called trust constrained. We can read the documentation on what it is. But here you require to specify, well, the bounds are the same, the cost is the same. Here you require a special function for linear constraint and special function for nonlinear constraints. So for the linear constraint, the function is right here. We actually specify only the coefficients of, in this case, let's see what it is. So in this case, we have, this is the linear constraint. So you can see x1 plus x2 plus x3 equals 5. So this can be written as copy. Okay, so this is written in the following way: x1, x2, x3, x4, x5 equals 5. And then there is a matrix, which a row vector, which multiplies with this to give 5. So 1 times x1, 1 times x2, 1 times x3, and 0, 0. So this is what SciPy requires you to give. This is A, and it needs you to give B. So if you go back to the code, the linear constraints are always specified. So this is only for linear, not for the non-linear. It's not possible to specify nonlinear constraints that fashion because you could have any kind of nonlinearity. Okay, so here is the constraint. So the A, which I wrote down, is 1, 1, 0, 0, and 5 is the lower bound, and 5 is the upper bound. So it's really specified as a nonlinear inequality constraint, but with the same upper and lower bound. So this is a very powerful method, because now if you have a constraint which is was actually an inequality constraint. So let's say that this was less than 10, but greater than 2, then what happens is you will specify 2 and 10, and that's how you'll take care of it. The nonlinear constraint is basically a nonlinear function, which actually is defined here: 5 minus x3 minus x4 square, x2 minus, and it's actually telling you the bounds again on that function. So remember that this we wrote down is greater than 0, so it can take a value from 0 all the way to infinity. So accordingly, this is specified. The first one, which is this one, is specified with a lower bound of 0 and upper bound of infinity. The other one, which is the other nonlinear constraint, is this one, because there's a square. That is an equality constraint equal to 5. So if you go here, it is specified as right here as equal to 0 with the lower bound, 0 with upper bound. So what this does is, this is a framework where it just puts all the linear constraints together or the nonlinear constraints together, unlike the other SLSQP, and then it just runs through this. So remember, this was the solution. You can copy this and put a notepad. Okay, so that's the solution. We can run this code and then check this against the other one. You sure I've copied this? Okay, so first value is 3, second value is 0.675, third value is 1.3247. The fourth value is 2.45, just agree, but the fifth value doesn't agree, but you can see it's very small, 1e negative 8, that's practically 0. So the fifth value is actually 0. So this is how you'll do optimization with this. Now, you can also read through the documentation. You'll see that some of these are for constrained optimization, some of them are for unconstrained optimization. So you might want to check them. Some requires gradients, which are the derivatives. Some don't require derivatives. If the function underlying phenomenon is non-linear, sorry, it's non-smooth, then you don't have gradients, and then you have to use some other method. So this is basically a primer on all the unconstrained minimization methods you can use: CG, BFGS, Newton CG, so on and so forth. And then these are all the constrained ones. So don't randomly use them, just go through the documentation to see which can be used. So let's see some applications of this in control. I'll just talk about 2 applications and not really give you the code. Well, I'll give you code for one of them. Okay, so the first one is inverse kinematics. Okay, so we've seen this problem a couple of times now. We have a robot which is trying to move in a path. And the way we did this was we used fsolve. What fsolve does is input goes in x reference and out comes theta, right? Theta for joint. This theta joint, and this is x ref. Now this will work as long as you have same degrees of freedom. So if you have a 6, this is 6 cross 1, and if you want to solve for 6 angles, that will work just fine. But what if you had more than 6 joints? What if you had 7 joints? So if you have 7 or more joints, you're looking at more number of variables to tune and less number of constraints, right? Because now what will happen is this function is going to be x ref. You want theta, you want something to map it. Joint. This is 6 cross 1, and this is maybe 7 cross 1. Some of the manipulators actually are 7 cross 1. So in this case, we have seven variables, and we have 6 constraints, which means that, or 6 equations. So if you have 6 equations and 7 variables, you have freedom of choosing one of the variable, right? This is where you will use minimize. Minimize will do it. So what you'll do is, for a problem like this, you will specify a cost, which would be perhaps be x minus x ref summation square. You're optimizing over, you're minimizing this cost. So minimize cost over x over theta. But it's not clear what x is. Well, x will come from your forward kinematics. X equals f of theta, forward kinematics. Okay, so you're trying to minimize that. Now you could, what you could do is you could put bounds. So you know that theta has a bound, theta min, theta max. Previously, it was not possible to do that with fsolve, right? But with this, you can actually do it. You can actually put bounds on theta. You could also, if you want, instead of specifying the cost like this, you could also define a equality constraint. So this would be bound, and this would be equality constraint. This is actually redundant. You have this and you have this. It's actually a better way to enforce the constraint because it ensures that all these are met. This is another way to do it. So you could do this with unconstrained optimization if you want to, but there's no guarantee that the cost will go to zero. Ideally, we want that cost to be equal to zero, right? If it's zero, then you know that x equals x ref. So you can play with this. Sometimes what they do is they'll replace this cost with trying to penalize. You could actually put just zero. There's no cost. There's just constraint. So it will just try to do it with. It's trying to do something like fsolve, but with more variables. Sometimes people put a cost which tries to. So another way people do the cost is they would just say theta minus theta average square. So they'll try to take the average of theta min and theta max squares in a attempt to get the solution to be close to the middle of the joints, right? You don't want the angles to be too much to the extreme position of the joint. So what they'll do is they'll specify this cost and then this constraint, and you're done. Or if you want to have redundancy, you could do that. That's either of this works. So here's another way of doing it. You could put this cost and this constraint, and then that will work too. So there are really many ways to put the cost, and eventually you want to do something which will help you. So here's one application. The other application is in motion planning. Okay, our caricature for motion planning is there is a robot which has two inputs, V and omega, and then there are obstacles, and then there is a goal. And then we know something about the obstacles. We know the radius or the location, the center of the obstacle. So let's call that rho 0. And then we know the radius of the obstacle. So rho 0, R0, rho 1, R1, and so on. Okay. So again, we need to specify a optimization problem. This can be done in numerous ways. One way is if you want to do totally unconstrained, or let's define a cost first. We could specify a cost as okay, this is x comma y, x minus xg square plus y minus yg square. So this is a cost. Minimize. This will be summed over the whole trajectory. So minimize cost. Here, v and omega as the minimization variable. So you minimize this such that you reach the goal. Now, how do you get x and y? For x and y, you'll have to do this. X dot equals v cosine theta. Y dot equals v sine theta. Theta dot equals omega. So you need to integrate this to compute x, y, and of course theta, but theta is not needed. So this will give you x, y as a function of time. And remember, this has to be solved over some time. The summation is over some time. So if you have to do this whole exercise in, like, say, 10 seconds, then the time will come there. Now, this cost only tells you to go to the goal, but what if you meet an obstacle? So what you can do is you can add a cost, which basically, so this one gets you to the goal. If you want to be away from the obstacle, you just take this cost minus R0 square. So this is a cost of getting inside one of these red circles. and you want to negate that, so that way you're trying to go as far as possible from that. So being far away from that will actually lower the value of that, right? If you are in, sorry, you don't need this, my bad, you don't need that. So you're trying to be as far as possible from the obstacle, and this will be summed over time, and there'll be another summation over obstacles. So I'm missing another summation. So minus, this is over time, and this is over obstacles. This should be I. And let me move this clutter down. Time, all obstacles. You could also do this, which is, you could, instead of specifying it this way, you could also specify 1 divided by that. That way it is, it's going to go to infinity, right? It's up to you. You could try anyway. So this is an unconstrained method of figuring out how to solve this. The other way to do this is to specify constraints. So you'll say that x minus xi square plus y minus yi square. This is for every obstacle. This should be greater than minus ri square should be greater than 0. So you're always out of that red dot. So really, you can mix and match, or you could just put them separately. It's really up to you. You have to see, run this and see how it works. Now, what happens in the real world is that if you're trying to plan over 100 seconds or a really long time, this method is going to fail, because then you're going to do a very big optimization. So what is done is, there's a method called Model Predictive Control, and I'll show you code for this. Which does the following. It basically, if you're here and there are, say, obstacles, it will take a window, a time window. So let's say our time window so over this time, it only sees these obstacles. So it will plan based on those obstacles. After some time, when the robot reaches here, there's a new time window, which will be this one. So this is t equals t prediction. So now the plan would change, because now you'll see these obstacles in the second plan, and in the original plan, you had these obstacles. So it basically keeps replanning as you go. And by making the problem, like using the small prediction horizon, you can actually do it in a completely efficient way. This is like if you're trying to drive on a road, you're not looking at cars which are 400, 500 feet away. You're just looking at cars which are 200 feet away. You make a plan. After you cross those cars, you make a replan, and that's what Model Predictive Control does. I'm going to quickly show you code, and we should be done. This is code which does differential drive car motion planning. So I'm going to run this without obstacles. And to make life easy, remember that I did this in motion planning. There are two inputs, velocity and angular speed. Just to make my life easy, what I did was I just put velocity equal to constant value, and only made the angular velocity be the optimization variable. So you can see it perhaps in the F minimize. Let's go to the minimize. So here I'm minimizing omega. I'm just actually minimizing one number, omega. That's it. Instead of minimizing omega over time, so having different omegas over, let's say, 5 timestamps, I'm just minimizing one omega over whatever seconds I choose to do it. So I do that, and then I get that solution as you saw. But then what I can do now is, and of course the cost is going to the goal. So the cost is how close I am to the goal. It should be here, how close I am to the goal. So the closer I am to the goal, the cost goes to 0. Now, what I can do here is I'm going to add obstacles. Okay, now the change I make in the code, and these are like some of the obstacles, is I just added one obstacle for now. So in the cost, if the obstacles are on, I take this cost, which is how close you are to the obstacle. I actually only add that cost if I'm very close to the obstacle. This is just to make it more efficient. So if I'm very close to the obstacle, which is given by a region R, which could be the radius of the obstacle, then I turn on this cost. Otherwise, it turns off. Now, this is not a smooth way of doing things, but it actually, in this case, works. I actually use the log of, it doesn't really matter. You don't have to take log. And actually, I have other ways of doing it too. So running this now with one obstacle, it should take a little bit more time because now that becomes no longer linear, it goes fine. We could actually add more obstacles and see if it does any better. So here is 3 obstacles. Okay, so now it decided to go to the left. It's a goal. Okay.